When executives envision the future of manufacturing, they often picture a darkened room where isolated, high-speed robotic arms have completely replaced human labor. But dropping a piece of advanced automation into a legacy production line does not create a smart factory. It creates a highly expensive piece of standalone hardware operating in a complete vacuum. No matter how fast that robot moves, it remains completely blind and mute. It cannot receive upstream instructions, and it cannot broadcast its status to the machines waiting downstream. A true smart factory is an interconnected data ecosystem. It is defined by three specific properties: connectivity between every node on the floor, complete transparency of the data generated, and the agility to adapt to that data in real time. To build this ecosystem, we are going to map out the 5 distinct architectural pillars required to make it function. We will also look at why violating the strict sequence of these pillars guarantees that your capital expenditure will fail. Ultimately, a factory's intelligence is not measured by the physical machinery bolted to the floor. It is measured entirely by the data architecture that connects it. Before purchasing any new physical automation, an organization must pass a mandatory diagnostic baseline known as the maturity model. The model starts at level 1, computerization, where legacy machines operate digitally but remain strictly isolated. The next step up, level 2, introduces basic network connectivity between those nodes. Once connected, the system shifts toward actionable insight. Level 3 achieves visibility, providing dashboards that answer what is happening on the floor. Level 4 adds transparency, correlating that data to explain why it is happening. The peak of the ecosystem is reached at levels 5 and 6. Here, AI models achieve predictability by forecasting future constraints, and the system reaches adaptability, autonomously rerouting production without human input. There is a strict, unbreakable rule to this progression. You cannot build level 4 analytical capabilities on top of level 1 infrastructure. Attempting to bypass the early networking stages leaves the core machinery physically incapable of passing data up the chain to the central system. When you force high-level, rapid-fire hardware to interact with a silent, disconnected infrastructure, the absence of this foundational data creates immediate, severe operational bottlenecks. Digital transformation is strictly sequential. Attempting to skip over the foundational sensory layers ensures systemic failure across the entire production line. Consider the case of Siam Precision Parts, an industrial manufacturer. Looking to force an increase in throughput, the CEO invested 3 million baht in a new robotic arm. Initially, it looks like a success. The new robot operates flawlessly, feeding raw material into a legacy CNC machine at a blistering speed. But the architectural flaw quickly reveals itself. The robotic arm represents a level 4 capability, yet the legacy CNC machine it feeds is trapped at level 1, completely devoid of network connectivity. Because the CNC lacks a network connection, it cannot signal its capacity limits to the robot. The fast-pulsing automation continuously fires material at a machine that cannot process it fast enough. The inevitable operational crash follows. The robot overfeeds the machine, the CNC suffers an overload fault, and the entire production line grinds to a halt. There is a secondary point of failure as well. Without warehouse software integration, human workers still have to manually push carts to remove the output, completely defeating the purpose of the initial automation. The final financial reality is stark. To prevent further line disruptions, the 3 million baht investment has to be powered down and taken offline entirely. Isolated hardware investments do not solve production limits. They actually degrade overall line efficiency by exposing and exacerbating the infrastructural blind spots you already had. Fixing a broken work cell requires a diagnostic intervention, starting directly at the bedrock, Pillar 1, the sensory layer. First, an IoT sensor is installed directly onto the legacy CNC. This routes into a SCADA system, which acts as a universal translation layer to break down proprietary data silos so different machines can communicate. This feeds into Pillar 2, memory. Local machine data is pushed upward into a centralized cloud network, establishing system-wide visibility. With the network live, we integrate Pillar 3, the analytical brain, and Pillar 4, the robotic muscle. The previously failed robotic arm is reconnected, but this time its programming is instructed to read the network signals. The operational fix is immediate. The robot now waits in standby, only feeding a new part into the line when the CNC sensor pings the cloud with a ready signal. Finally, this interconnected data stream must be wrapped in Pillar 5, the immune system, which enforces rigorous cybersecurity protections and ESG protocols. Contrast the synchronized bidirectional operation with our earlier case study. By establishing communication between the nodes, the physical bottlenecks are entirely eliminated. Advanced hardware only generates its intended return on investment when it is fully embedded within a continuous, bidirectional data loop. Mapping this out on the factory floor is only half the process. Technology alone cannot sustain this architecture without the correct organizational structure supporting it. Manufacturing plants traditionally separate into two distinct camps: operational technology, the engineers who manage the physical machinery, and information technology, the programmers who govern the digital data flow. If these two departments remain siloed, the five-pillar ecosystem will never be realized. Executives can test their progress with a simple diagnostic. True convergence is achieved only when machines from completely different proprietary vendors display their output on a single, unified screen. A functional smart factory requires both OT and IT departments to sit at the same table and co-author the production system from the ground up. Technical connectivity on the factory floor is impossible without first achieving organizational alignment in the boardroom. This brings us to the final architectural goal. A smart factory's primary objective is not merely the reduction of human labor. Building a system specifically to minimize headcount results in a rigid, brittle facility that fractures under supply chain pressures. The ultimate target is Level 6, agility. Here, interconnected sensors and centralized data allow the factory to autonomously adapt to unforeseen disruptions. If a supplier is late with raw materials or a specific machine throws a fault, an agile system instantly recognizes the delay and automatically reroutes the production queue to keep the line moving. Before you sign off on any capital expenditure for physical hardware, you must rigorously audit your existing data architecture and determine your precise maturity level. Building an interconnected ecosystem has to begin by giving your legacy machines a voice. In our next analysis, we will examine exactly how that is done by exploring the first pillar, industrial IoT and SCADA integration. This brings us to the final architectural goal. A smart factory's primary objective is not merely the reduction of human labor. Building a system specifically to minimize headcount results in a rigid, brittle facility that fractures under supply chain pressures. The ultimate target is Level 6, agility. This is the state where interconnected sensors and centralized data allow the factory to autonomously adapt to unforeseen disruptions. If a supplier is late or a machine throws a fault, an agile system instantly recognizes it and automatically reroutes the production queue to keep the line moving. Before you sign off on any capital expenditure for physical hardware, you must rigorously audit your existing data architecture and determine your precise maturity level. Building an interconnected ecosystem has to begin by giving your legacy machines a voice. In our next analysis, we will examine exactly how that is done by exploring the first pillar, industrial IoT and SCADA integration.